Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
So cute. Hi, everyone. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to the universe, and a friend to...
Me.
Yes, it's you.
I'm Corinne Caputo. I'm a writer and a funny person and a friend to the universe. Friend to all, really.
Friend to all. Even those who don't deserve you, Corinne.
Yeah.
You're a good person like that.
That is true. No, I have some great friends, and I'm really grateful for them. Especially our listeners. And I just love where we are today. This is where I made a lot of my first friends.
Oh, yes. This is your...
Yeah.
Okay. All right. So tell the readers about it.
This is my elementary school.
Tell the listeners about it.
Let's tell the readers. This is my elementary school on Staten Island. We are in one of the quieter classrooms. This is still an elementary school, so they all have like little libraries in the rooms. So we're sitting around in some beanbag chairs, and there's some kids playing outside, and maybe we'll hear some kids pass in the hallways. But this is a place that really taught me to be excited about learning and about socializing. Oh. And once Henry Winkler came in 5th grade to be principal for a day.
Oh my gosh, the Fonz was your principal for a day. That's so exciting.
Yeah, and I didn't know what that was.
Of course not.
But my parents were like, you have to wear your leather jacket tomorrow. I didn't have a leather jacket, but it was like, he's coming to school. And I remember he told the girl next to me he liked her hair, and I was pissed.
Oh, come on, Henry, just turn like one more degree to the left.
I know, I was like, oh, you don't see the magic inside me just from me quietly sitting here well-behaved?
How dare he?
But yeah, I thought this was a good spot to talk more about school.
About school, yes. More specifically, listeners, we're going to be talking about my school. I love talking about myself. This is our 54th episode, and I realized that I've never explained to you what research I did to become a doctor of the universe. I've mentioned that I studied exoplanets. I've mentioned that I studied the galaxy, but I think this is the time to get more into specifics. So I will talk about, like, very briefly, the research I did in undergrad, but most of this is going to be about my PhD research that made me a doctor.
Yay!
So I'll start with the undergrad research. I didn't find astronomy until my sophomore year of college. And once I did, I didn't want to be pigeonholed into a specific area or a specific subfield of astronomy. I knew so many people who like did their first research project in star formation or whatever, and then they studied star formation for the rest of their careers. And I didn't want to do that. I wanted to find the subfield that I was most interested in. So my first research experience was the summer after my sophomore year. I did an internship at the National Radio Astronomy Observatory in Charlottesville, Virginia. Shout out to any listeners we have in Charlottesville. And there I was studying a specific galaxy called IRAS 08339 plus 6517.
Oh, yeah. I know that one.
Yeah, it's a name that rolls off the tongue. I was listening to a lot of Toto that summer, so I nicknamed her Rosanna, and I called her Rosie for short.
Oh, I love that.
I was looking at spectroscopic data, trying to figure out some of the physical properties of this galaxy, and I actually got the spectra of 3 different spectra from that galaxy tattooed on my leg that summer. And that was fun. I learned like the temperature of this galaxy. It was about 250 million light years away. So then I had experience studying the spectra of galaxies to learn their physical properties. So the next summer, someone at the Harvard-Smithsonian Center for Astrophysics asked me to do the same thing, but on a collection of galaxies instead of on just one. So I did that, but at the same time, I was doing an internship at something called the Banneker Institute, which was for Black undergrads in astronomy. And there I was doing my first exoplanet research project where I was studying the eccentricity of Kepler 186f, which I listed in our AMA episode as my favorite planet because of that research project. So I was doing 2 projects at once. and it was a lot. Both of my advisors were like, that's not a good idea. And I was like, screw you, I need money.
No, it's fun. Yeah. Yeah.
But it did work out pretty well. I would do one in the mornings and one in the afternoons. And they worked on kind of different time scales. Like I would set a simulation running in the first one in the morning, but it would take a whole day to run. So when I went back the next morning, it would be done, like that type of thing. That was my second summer as a researcher. But then in class, there were also a lot of opportunities to do research projects. So I did an instrumentation lab where I built an actual detector. It's not really a telescope, but it was a detector that could collect signals from the cosmic microwave background, which is the radiation left over after the Big Bang. I did a project where I used VLA data, we've talked about the VLA, to study this cloud that was actively forming stars. I used the Chandra X-ray Observatory, which we're going to talk about in a few weeks, to study a specific black hole that was really active and bright, so we call it an active galactic nucleus. And I did another exoplanet project for my senior thesis. So I did research in almost all of the subfields of astronomy that I could get my hands on. The only thing I didn't really hit was like transient stuff, so supernovae research. But at the end of that, I knew what I liked and what I didn't like. I knew I loved the intuitive nature of studying exoplanets. It's really just a bunch of like algebra and geometry. And like if you can visualize the planets going around the star, you can develop a pretty good intuition for that subfield of astronomy. I knew that I liked how rigorous galaxy stuff was. Like all of the galaxy researchers that I knew, they were really good at math and they were really good at coding, and they had to think about these really cool physical processes going on, like where there were so many different competing factors. Like it was a very complex system, and I was attracted to that. But I also loved thinking about change over time. So I knew I wanted to get that in. And what that left me with was a specific question where I knew there was a place around stars that was good for life. We call that the habitable zone or the Goldilocks zone. That's the place where the temperature is right for liquid water. Any closer, the water would boil away on a planet. Any further away, and all the water would freeze. So I knew about that concept around stars, but I wanted to know if there was something similar for galaxies, like if there's a galactic habitable zone. And I didn't see that answered anywhere in the literature or in my classes, so I decided to go to a PhD program specifically to answer that question. Otherwise, I don't think I would have gone. I didn't want to go to a PhD program just because it was the next step. I wanted to actually be motivated by curiosity. So that's what I wrote in my applications to grad school, and then I got in, and that's what I ended up studying. I chose projects that would give me the knowledge and the skills necessary to answer that question. So I was like very strategic once I got to grad school.
Yeah.
Corinne, do you have any sort of impression in your head about what grad school is like?
You know, for STEM, it's a little harder for me because a lot of the grad programs I considered, because I feel like a lot of people are like, I'll just go to grad school. I won't figure out like what I like. I'll just continue this kind of academic calendar, which, or at least that's what it was for me, was largely about like creative fields or writing or things like that. For STEM, it's a little foggier, and most of it's come through our conversations. It seems like a place that's like very research heavy, but also kind of traditional, at least in terms of like social rank.
It's hierarchical in that way.
But I know that some people had a great time, and a lot of people I know didn't like it.
Yes.
Which I guess is true of anything, so I don't mean to be vague, but like I think it can be kind of polarizing thing.
Yeah, I think that's true of academia broadly. There are a few things about STEM PhD programs that are different than humanities PhD programs. For example, most, not all, but most STEM PhD programs will pay you pretty well. I think for most universities, the same isn't true in a lot of humanities programs. But yeah, you got it. I'll take you through like the schedule, I guess. So you get to grad school. First of all, to get in, the application process is very similar to applying to undergrad. You write a few statements and essays. You fill out information about the education you have up until then. You say what you're interested in studying. Instead of taking the SAT, you take the GRE, which is the graduate research exam. There is a subject-specific one, so I had to take the general GRE and the physics GRE. That's being phased out of admissions now. A lot of astronomy programs aren't taking the physics GRE score, and they're like not using it in admissions, which is good. Yeah. Because it has been shown over and over again that your score on the physics GRE does not correlate to your success as a scientist or whatever. For example, I took the physics GRE twice, and I think my best score that I got on it was in the 7th percentile.
Yeah.
So I did not do.
How were you feeling when you got that score?
I felt like literal poop.
Yeah.
I felt like the shittiest human being.
Yeah.
It was demoralizing to be told over and over again.
There's so much weight.
Yes. People tell you this is like the most important test of your career. And so there's a lot of pressure on you. The test itself is multiple choice. It's 3 hours. I think it might be 180 questions. Multiple choice physics exam.
Yeah, that's hard. That's hard to sit for. That's hard to just do prep for. I mean, I'm sure it's a lot like the SATs. I just got a Times alert today on my phone that was just like, again, proving that your generational wealth kind of is directly related to your scores on these kinds of tests, which is not representative of how you'll perform as a student, and also keeps like white people in power and not like a broader student body. So these tests are just problematic in a lot of ways. Mm-hmm. I remember the most nervous I ever was in my life was sitting for the SAT.
It can be so nerve-wracking.
And it's just so much pressure for like you to perform such a specific, I don't know. Just, I hate it.
It's a very specific set of skills that they're actually testing. Like your ability to take a standardized test is more of what they're evaluating instead of like your actual knowledge of the material.
It's like Henry Winkler coming into the classroom and not seeing everything about me, not seeing the amazing person I am because he's just looking at hair.
Yes. Standardized tests are Henry Winkler.
They're the Henry Winkler of tests.
So you get in based on your GRE scores, your grades, your research experience, letters of recommendation. And then when you get to when you start your program, typically you'll have 2 or 3 years of classes, of graduate level classes. For me, there were something like 8 required classes, and then I had to fill it in with electives, and then there was a research component, because in my program, at least, we started research right away. So we were doing research and classes at the same time for the first couple of years.
Oh, okay.
So my classes were in like, here is the interstellar medium, or the space between stars. This is stellar structures. There was a class on galaxy evolution. There was a class on radiative processes. So like, how does radiation actually move through space? I took a class in climate. That was one of my electives. I think I took a stats class that was an elective. But most of the time was spent on research. It was made very clear that, at least in my program, others are different, the focus was on research. That's what they wanted me to prioritize. Yeah. After my first 2 years, I did research full time, and I published 3 scientific papers, almost 4, but 3 was the minimum number that I was told I had to have before I could graduate. And my dissertation, which is like the big paper that you write at the end of a PhD program or a master's program, but sometimes they're called a thesis. My dissertation was all of the papers I had published, basically like stapled together with some connective tissue and an introduction and conclusion that explained like what big question was I trying to answer.
Yeah.
So do you want to go through the project?
Yes, let's do it.
I know usually when we're like covering a scientist's work, first of all, they're dead. I am very much not dead. But when we cover another scientist's work, we usually play this game at the end where we're like, guess if this is a real paper or not. And I like to do that because I loved to give my papers fun titles. And so you will see that because the first paper I ever wrote was called Finding Mountains with Molehills, the detectability of exotopography.
That's really fun.
Thank you.
See, you were always
Thank you.
thinking like a science communicator.
Oh, literally always. Yeah, I knew, even when I was applying to grad school, I said, I want to study the galactic habitable zone, but I really want to do science communication.
Yeah, that's really cool.
Yeah, and I was, part of it was fortune, part of it was intention on my part. I had an advisor who was very passionate about his own SciComm, so he was more accepting of me doing mine.
Yeah.
So exotopography is a word that I made up when I was doing my first research project. It is the topographical features on an exoplanet and like the study of those topographical features. So we've talked about transit photometry before. I am a transit photometry girly. I absolutely love looking at the shadows that planets cast on their host stars. There's so much we can learn. Typically, what we've learned since the 90s using transit photometry is how big the planet is compared to its host star, how far away it is from the star. Then we can get an understanding of the average temperature of the planet. But we never had any way to figure out what the surfaces of those planets look like. And early on, in like my first or second week of grad school, my advisor, David Kipping, he was throwing out a bunch of potential research projects, and one of them was, what if we can find a way to figure out what the surface of an exoplanet looks like using transit photometry? And the idea was that if you have a powerful enough telescope, it would be able to see the very small changes in the shape of that planet's shadow as it passes in front of the star. But you need really, really powerful telescopes, because even if you take the Earth with all of its mountains and trenches, like what's the biggest mountain here?
Everest?
Everest, thank you. I was like Olympus Mons, but that's on Mars.
That's the Mars one.
It's the Mars one. Even with all of our mountains, if you took the Earth and you scaled it down to the size of a pool ball, the Earth would be smoother than a regulation pool ball.
Whoa, really?
Yeah. Yeah, because mountains look really big to us, but compared to the size of the Earth, they're quite small.
Yeah, that's fair.
So mountains or other features would also be quite small compared to other planets, meaning it's theoretically possible to see the changing silhouette reflected in the light curve, but you need a really strong telescope. To do this project, I first wanted to see if it was feasible to detect it. So what would the rocky bodies in our solar system look like? What type of light curve would they create if they were rotating in front of a star? So I got elevation data for Mercury, Venus, Mars, the moon, from the U.S. Geological Survey website. And then I got elevation data for Earth from the Shuttle Radar Topographic Mission database, all publicly available. So I had those bodies and their elevation data. For the Earth, I actually got pretty clever, and I had regular Earth with the oceans, but I also figured out what it would look like without any oceans. Because there are a lot of surfaces that are covered underneath the water, and I simulated their transits. And I found which was the bumpiest planet, which was the least bumpy, and I created a new unit called bumpiness, just like so, just like so unofficial. But you can just apparently you can just do that. So I created this new unit of bumpiness, which was like the standard deviation of all of the topographical heights on a world. And I created this equation that you can use to go from the amount of scatter in your light curve to the bumpiness value of the planet that you were observing. We determined that this type of observation would work best for a Mars-sized planet in front of a white dwarf, because you want a smaller star, because then the surface features are blocking a larger fraction of the star's light, so it's easier to see in the light curve.
That makes sense.
And then we did like a whole feasibility study. We imagined if you were to do a survey mission where you're just scanning the sky for one of these types of systems, what type of telescope would you need and how long would it take? And we determined that for like the worst case scenario where these types of systems are really uncommon and some of them are pretty far away, we would need about 10 hours on the biggest telescope in the world. At the time, the biggest planned telescope was the overwhelmingly large telescope. It's 100 meters across. That has since been canceled. So we would need to use a smaller telescope, like the extremely large telescope or something that's only 30 or 40 meters across. And with that, we could do this type of survey mission with, I don't know, a couple dozen hours on a telescope like that. A couple dozen hours is a long-ass time.
Yeah, that's a long time.
It's a long time in astronomy telescope world. So we're not doing this anytime soon. This whole project was really just like a proof of concept that such a method could one day be possible when we have better technology and a better understanding of what types of planets are out there. But one day we'll be able to do this. And it's not just fun to figure out how bumpy a planet is. If we had an idea of how bumpy its surface was, we would be able to infer some things about internal processes, because mountains and volcanoes, they form through tectonic plate movement. So if we see a planet that looks like it has a lot of mountains and volcanoes, we would know, or we would be able to guess that it probably has some internal tectonics going on and maybe volcanism and stuff like that. If we can see the same features appearing in the silhouette regularly, then we can get a sense of the rotation period of the planet. There's not actually a reliable way right now to figure out the rotation speed of a planet, because they're very small.
I didn't know that. Yeah.
So with this technique, we would be able to infer that. And we'd also be able to infer if there's an ocean or clouds. We made a plot of planet bumpiness versus its density. So there is that relationship. Like if you have a really dense planet, its gravity will be very strong. So it will be harder for it to get higher topographical features. Mm-hmm. So there is that relationship between density and the height of the feature. So if you see a planet that is less bumpy than you expect it to be based on its density, then that's a sign that something like an ocean or clouds is blocking the surface features from our view.
Oh, cool.
Yeah. So that's what that whole project was about. I had a little bit of trouble publishing that paper because it's kind of like a lot of people were like, why do we care about this? We won't be able to do it anytime soon. But my advisor and I were like, okay, but we should still know about it.
Yeah.
So that was my first published paper.
Thrilling.
I'm wondering, what do you think is the bumpiest planet?
Well, I mean, we mentioned it before, but I know that Mars has the tallest mountain. So I don't know if that one tall mountain makes up for like however many mountains Earth might have, but I feel like it might be Mars.
Yeah, it is.
Oh,
it's
cool.
Totally Mars. Mars is by far the bumpiest planet in the solar system. Right after that is the moon. And then right below that is the dry Earth without any ocean. And I thought it was really interesting that even though Earth has like the Marianas Trench and like all of that stuff, it would be Mars. The thing about trenches is that they are less likely to show up in a light curve. So like they're less likely to show up in the silhouette because they're a dip,
it's down,
right?
Yeah.
So we also address that in the paper. We address possible sources of like false positives, things that could artificially increase the bumpiness or artificially decrease the bumpiness in the signal. So like that's the whole thing about a scientific paper. Like you have to cover all those bases.
Yeah. That's a lot of thinking. That's what I think grad school is. It's a lot of thinking.
And that was just year one of thinking. Yeah. For year two, I decided, all right, I understand exoplanets. I know that side of habitability. Now I need to focus more on stars, because in order to understand a planet, you have to understand the type of star that it orbits. And I also wanted to learn more or get more comfortable with machine learning. Machine learning and artificial intelligence, when I was in grad school, they were becoming more popular tools, and I wanted to figure out how to use them. So this next project, I actually never published a paper for it because it took forever. But if I had published a paper, I would have called it Birds of a Chemically Homogeneous Feather Flock Together.
Yeah, I think we need to play a game where it's like, did Moiya come up with this title or not? And I think it's going to be easy.
Yeah. This is what I called all of the talks that I gave about that research project. So for this project, I was studying stars, specifically their position, their velocity, and their chemistry, to kind of reverse engineer the behavior of the Milky Way galaxy. This is a subfield of astronomy called galactoarchaeology. It's essentially people who use chemistry and motion of stars to figure out what the Milky Way was doing billions of years ago, or like over the last 10 billion years. So I had position, velocity, and chemistry data for stars. And I was, here's like the context. Here's the info context around this project. Most stars are born in groups. Groups of like 1,000 to 10,000 stars. We call them clusters. But these clusters can break apart for a few different reasons. And each of these mechanisms for breaking apart has its own chemical signature or its own chemical fingerprint. So if you can look at the chemical distributions of these groups of stars, you can figure out how they formed. And there are 3 different ways. One of the ways is that you can basically like gather stars in from the halo. The halo is this big cloud that surrounds the Milky Way galaxy, and there are a bunch of like little satellite galaxies in there. There are some clusters of stars. There's a lot of dark matter out there, but the Milky Way's gravity can pull stuff in from that halo, and that will stretch out the group over time so that you see these streams. I did a couple simulations where I saw the streams of stars, and they're pretty beautiful. But the chemical signature there would be that it has, a narrow range of chemistries, and that chemistry should look like the chemistry of the halo, which is like not a lot of heavy metals. Mm-hmm. And then the second way is that you can just like through gravity working over time as the stars orbit the galaxy, those clusters can just dissolve because they aren't gravitationally bound to each other. And if that's the case, then because these stars form together, they should also have very similar chemistry, but it should look like the chemistry of the disk, so more metals, more heavier elements. Mm-hmm. And then you can get these groups through something called resonance with the spiral arms and the bar of the galaxy. Essentially, as the spiral arms orbit, they can give some stars a push ahead, and they can drag some stars back. So you end up splitting these groups apart that way. And that should have just kind of like a chaotic chemical signature because it's not coming from stars that formed in the same place. So that's what I was looking for. I used the machine learning algorithms to cluster these stars based on their motion and their chemistry. And I never published a paper because we just kept getting so bogged down into the details of exactly how I was analyzing their chemistry and which database was better than the other. And I had 3 different advisors on this project, all at different institutions. And it was just a whole mess.
Yeah.
A whole mess. But it was fun.
So annoying. Yeah.
And I learned a lot.
Well, good.
Yeah.
I'm glad, as long as you enjoyed the journey.
I mean, it was still grad school.
Yeah.
And so I still cried a lot. I built a little nest. A crying nest under my desk.
Aww.
But it was fun for a research project, in my opinion. And so my question for you, Corinne, do you have any questions about the project?
Well, not about the project, but I'm curious if a lot of your cohort was also just so frustrated with some of the grad school process.
Oh, that's a great question. My class was pretty small. The average class size in my department was about 5 people.
Oh, wow. Small. Yeah.
But because the year ahead of me was so big, my class only had 3 people, and we were all women.
Oh, fun. But
which
also,
was amazing.
Maybe a lot of pressure.
No, yeah, probably. Like, they're definitely inherently. But, like, I don't know. We got pretty close, and we kind of weathered the storm together.
Yeah. Oh, that's good.
But I'd say there were some people, especially in the year after me, which was, I think, 4 guys and 1 woman.
Oh, that's worse. That's bad.
Many of those guys were very physicsy. And there's a kind of a stark divide, I think, between like physics people and astronomy people. Physics people tend to be more intense. Mm-hmm. The guys in the class below me were all very physicsy, and many of them loved grad school. Like, had the time of their lives.
Yeah. Interesting.
I and everyone else in my cohort and the woman in the cohort below me, we all hated it and got out as fast as we could. I think of my class, only one of them is still in academia. The 2 of us left, and then the woman in the class below me, she also left academia. Well, she's getting her master's in business, but she left astronomy.
Wow, to totally leave the field. Interesting.
Mm-hmm. Yeah, it does not foster a lot of goodwill with the people who go through. So many people end up leaving.
That should feel sad to them. To the people in power, I feel like a contrition rate that high is really bad. Yeah.
Mm-hmm. I agree. They like to talk about the leaky academic pipeline a lot. So some people are trying to fix it, but the reality is that the number of people going through astronomy PhD programs is way higher than the number of jobs there are like for astronomy faculty at university. Yeah.
Totally.
It's a total mismatch. The system is kind of broken and we need to do a major overhaul.
And that's why we're announcing the Pale Blue Pod University, where everyone has a job and and writes fun papers.
I wish. One day, by the time we make our 500th episode.
Yeah.
PBPU. So to go along with this research project, Corinne, I have a question for you. Ooh. Imagine, because we're recording this still during spooky season, you're going on a walk through an enchanted forest and you come across a little cottage. A woman walks out of the cottage. Of course, she is a witch. Whether she's good or bad, I'll leave that up to you. But she asks you a question. She says you have to choose a chemical element that she will use to make a bird. Like the bird will be the avian embodiment of this element. And she asks, what element are you choosing?
Whoa. Okay. There are so many cool elements. But in 7th grade, I did a large research project on sodium.
Oh.
And it became a very special element to me.
Aww.
So I feel like I'm going to pick Na, sodium.
Okay, but like,
Salt
what
bird.
would a sodium bird look like? Yeah.
Saltbird shows up when you need him to salt your food. Saltbird lives in the ocean and in the air. And is really used in, like, ratatouille style in restaurants.
Oh.
You don't eat the bird,
yeah,
but he's around to finish your plates.
To salt them. In order to get that, do you, like, grab the bird and wring it
Moiya
like a
is wringing her hands like a pepper mill. And that is not what I'm picturing, because that feels deadly. I think Saltbird just, like, shakes his wings and some salt flies off, which now sounds disgusting, because that feels like dandruff or something, but...
Yeah.
This is the witch made this bird. It's not going to have a happy life.
Corinne's like, it's not my fault. It's the witch. The witch did it.
It's not my problem. The witch wanted to create a monster. I'm trying to make him useful to society.
Okay. Excellent choice. I think I would have gone with something like, I really love gallium. It's the one that its melting point is your body temperature, so it just like melts in your hand.
That's cool.
And to me, that would give the bird some like shape-shifting abilities. Like it could melt itself down and then reform. Like its base form is a bird, but it can also...
I would love a neon bird, but like I know that neon without like other stuff is just like a gas, but that cool color is because we've made it so, but... I would love a neon light bird. I think that could be fun.
Especially since birds are so flashy in real life.
Yeah. There's going to be one bird that really would love that.
Yeah.
Hey Hey there! It's a great time to thank our patrons who support the show every single month. So thank you, as always, to our Sun-like stars, Sharn Llewellyn, Lissa, and Ian O'Leary. And you can support us, hear your name on the show, and make it to the patron star chart, all by supporting us on Patreon for just about $1 per episode. If you sign up for an annual membership, you get a 13% discount. Find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to the source at patreon.com/palebluepod. And if you can't support us financially, that's totally fine. We love you very much. You can support us by reviewing the show on whatever app you use and by sharing the show with your friends. And before we get back to this show, I want to recommend another pod in the Multitude family. Spirits is a history and comedy podcast focused on everything folklore, mythology, and the occult, told through the lens of feminism, queerness, and modern adulthood. Every week, mythology buff Julia and her childhood best friend Amanda get together to learn about a different story from mythology and folklore over drinks. That's everything from the mythological origins of major franchises like Lord of the Rings and Wonder Woman to modern urban legends to a roundup of werewolf stories from around the world. There are even episodes that Moiya and I have guested on. Start listening with any of the over 300 plus episodes they've released over the last 6 years. And whether you're here for analysis of mental health and mythology or creepy modern ghost stories, there is so much to enjoy, and I know you'll love it. Dive in at spiritspodcast.com or search for Spirits wherever you download your podcasts. Okay, back to the show.
All right, so my next paper, this is my third-year research project. The inspiration for this project came from one of the members of my dissertation committee. His name's David Helfand. Look him up. He looks just like Santa. This was common knowledge in the department. We, instead of, whenever we were talking about David Helfand in the student group chat, instead of saying his name, we would just send a picture of Santa. Like that, he looks like Santa. He told me that one day he was in the shower, which is where most great scientists have their best thoughts, and he was wondering if there's any relationship between the speed of a star and whether or not it can host a planet, because he knew that I was very interested in the dynamics of stars and the habitability of planets. He was like, here's this intersection that I'm curious about. Let me tell Moiya. And he did that day after his shower. And then I ran with it, and it became my third-year research project. This one is my second published paper. It was titled Not Gone with the Wind.
Oh my God, that's so fun, Moiya.
Planet occurrence is independent of stellar galactocentric velocity. It really is the fun part in the beginning, and then just like the nutritious part at the end.
Oh, that's so fun.
All of my paper titles were like having your dessert before dinner.
Yes.
And so for this project, I compared the velocities of stars that hosted planets to the velocities of non-host stars. And at first, I got what I thought was a very exciting result. I saw that the stars that didn't have planets moved faster in their orbits around the galaxy than the stars that did have planets. And I was like, well, that's what I expected, but that's weird. Why? And so for months, I was going around trying to get people to essentially like prove that I was wrong, that this wasn't actually an effect I was seeing. Because if this were true, then the only explanation I could think of was that like fast stars are more likely to have dangerous interactions with other bodies. Maybe they move so fast that the pressure of moving through the gassy galaxy just strips planets away from their stars. I was like, that would be an explanation, but it doesn't seem very likely. And so I spent months trying to prove myself wrong, looking at all of the effects I could think of. And it turned out that it was not a true effect. Through those conversations, I learned that it was just an observation bias by the Kepler spacecraft. I should tell you that the data I had, in order to determine which stars had planets, I used the database from the Kepler spacecraft that looked for thousands of planets. And then to know how fast the stars were moving, I used data from the Gaia spacecraft, which we will one day definitely do an episode on. but that gave me the positions and the velocities of stars. And it turned out to just be a bias of the Kepler machine and a consequence of what direction Kepler is looking in. Because Kepler is, or not anymore, but it was staring in a direction that is like kind of angled towards the center of the galaxy. Not totally, but like 10, 20 degrees towards the center of the galaxy.
Yeah, yeah.
And it turns out that the host stars were just a little bit closer to us on average than the non-host stars. And that's because it's easier for Kepler to see planets around stars that are closer to us because they're brighter. So like there's that observation bias. So the host stars are just slightly closer to us, which means they are ever so slightly farther away from the center of the galaxy. And as you move away from the center of the galaxy, stars' orbits slow down because they don't have to move as fast to avoid being like pulled into the center.
Mm-hmm. Mm-hmm.
So it wasn't that fast stars lose their planets. It was just that we are seeing the easy targets, and the easy targets are closer to us, so they are further from the galactic center, so they are moving more slowly.
Yeah, yeah.
Mm-hmm.
Cool.
And the way I figured this out was in such like a weird, indirect way. I had to make a sample of stars that didn't host any planets, but they were identical to the planet hosts in every other way. So for every planet host star, I found another non-host star that was the same temperature, the same brightness, the same distance from the center of the galaxy, and I created that sample of twins, and then I compared their velocities, and there was no difference.
You cracked it.
But I cracked it. But I got to make a lot of very cool plots and graphs. It was very fun. Overall, this was kind of a null result. This was like, hey, community, there's nothing really interesting here, but look out for this one very specific effect of the telescope if you're looking to answer this specific type of problem. Like it was.
Yeah, totally.
But I published the paper, and it made me want to look in a more chaotic, faster-moving environment than our neighborhood of the galaxy. So I turned my attention to the center of the galaxy, which is called the bulge, and that's what my fourth and final project was on. But before we get to that project, Corinne, this paper was kind of a null result. So it was, in my mind, like a very cool take, you know?
Yeah.
So I would like to know, what is your coolest take? By which I mean, what is your most uncontroversial opinion that you think other people don't have?
That I think other people don't have, that I have. Let's see.
Yeah, but it's like it's not weird to think that.
So lately I'm in a phase where at the end of the night, before I sit down to watch TV, I will pour a seltzer in a glass and put a dash of bitters in it.
Ooh.
And it's really good. And and I'm just thinking of it as like just like a cozy little take is like, I feel like that's the coolest take of all. It's like, to get cozy,
Yes.
I like to put on a pair of socks. And it's like, okay. And that's kind of how I feel. My bitters and soda at night is like a little, all right, have fun.
OMG, that's exactly the type of thing I was looking for. I would hope you would have like a little tip of something you enjoy that you think others might enjoy, but they just don't know about it yet. So thank you.
Just put a few. I do 3 dashes of bitters and science.
Okay.
I have science incoming. If you put the bitters in first and then pour the soda, it foams up like a kind of root beer float. You know how like you get that foam? But if you put the bitters in second, no foam.
That, Corinne, remember our episode on fluid dynamics and turbulence versus laminar flow? By putting the drops in first and then adding the fizzy soda, you are increasing the turbulence and the mixing.
Yes.
Whereas if you do the drops second, it just has to rely on gravity, like bringing it down to mix it. No real fizz.
Okay. I do science every night.
Yes, you do. And most people do too.
It's very cute. That is my favorite thing. My husband and he'll pull out 2 cups at night, and then we each get one. It's very cute.
That's freaking adorable. I love that. This next project I did in my like 4th and 5th years of graduate school. I was definitely working towards a career as a full-time science communicator. But I think that definitely in my 5th year of grad school, I was essentially doing SciComm full-time, and then grad school was my side hustle.
Yeah, sure.
Yeah. I unfortunately wrote this last paper at a time when journals were kind of cracking down on fun titles.
Aww.
So I had to give it a boring title, and the boring title was something like 8 in 10 stars in the galactic bulge experience a close dynamical encounter every gig a year. It was like something really boring like that. Had I been able to give it a fun name, I would have called it Kicks in the Bulge, like 8 in 10 stars experience whatever, blah, 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 blah. Because the whole project was looking at the bulge of the Milky Way, which is this central region. About 30% of the stars in the galaxy live there, but they are much closer together than they are here in the disk where the sun lives. And they don't move on circular orbits. They move on these like weird rosette shapes. So like interweaving figure eights. Some of them are big boxes where like they do actually take sharp turns. Like one of the most challenging but most enlightening things I ever did in my grad school classes was learn how to simulate the orbits of stars in different, we call them gravitational potentials, but like based on how the mass is distributed, where does gravity push things? Because gravity is going to push you towards the center of mass. And in a spherical system, that's easy. The center of mass is in the center of the sphere, but the bulge it's not that simple.
Yeah.
The center of mass is not always in the middle. So like things are moving in weird orbits. For this project, I simulated the orbits of 1 million stars. And at every step in the simulation, I tracked its position, which meant later on I could calculate the distances between all the stars. And after the simulation, I went through and I counted how many close encounters there were. Close is relative, so I was looking for like a couple different distance markers, but the one I paid most attention to was encounters within 1,000 astronomical units. 1 astronomical unit is the distance between the Earth and the Sun, so these are 1,000 Earth-Sun distances. If something were to pass within 1,000 AU of our sun, it would still technically be within the solar system because the Oort cloud, that big cloud of debris that we've talked about before, that goes out a couple thousand AU.
Oh.
Yeah. So 1,000 AU feels really big, but it's actually pretty close in, like, relatively speaking, in the universe. And after I counted all of those dynamical, like close gravitational interactions, what I found was that 80%, 4/5 of them, have these close 1,000 AU encounters every billion years. And that's just one encounter. Half of stars have dozens of these encounters every billion years. So what I found in my 4th project was that these encounters are pretty common. Mm-hmm. They're dangerous because they can like rip planets away from their host stars. If it happens early enough, the planets might not form at all. But it can also be pretty sneaky. Like, so you can have a star that passes by and it just tugs a little bit on one of the planets, so that 1 million years later, its orbit is out. It either gets flung out of the system or it careens into its star. Both of those would be bad. So if we're looking for habitable places in the galaxy, we probably should not look there because there's a lot of messy dynamical stuff happening.
Wow.
So that was project number 4.
That does feel really messy.
Yeah. Yeah.
I feel like we've talked about that briefly before, of like something can pass by and pull. Oh, on the scary episodes, right?
Yes.
Scary things.
Yeah. I will always bring it back to this. This was one of my favorite projects that I did in grad school, and it was the last one. But that leaves me with a question for you, Corinne. Knocking a planet out of its orbit 1 million years after you pass by is like so sneaky rude.
Yes.
Almost petty, if you will. And so you don't have to reveal everything. You don't have to tell us your business, Corinne. But what is the pettiest thing you've either done, or if you don't want to tell us your business,
Love that.
What's the pettiest thing you can imagine?
Okay, well, there's one specific thing that happened to me that I'm thinking of. When I was living in New York, this is pre-COVID, I had spent the morning getting an IUD.
Oh.
which is a painful and very annoying thing.
Yes.
But the nurses and the doctors were so kind to me, which, like, for anyone who lives in New York, I feel like you're switching doctors a lot, or like you're always going somewhere. It was hard to have a relationship with any of them. And then you never know, like, if this person's going to be kind to you or like so exhausted or so whatever. So I had a lovely experience and I was in such a good mood leaving despite like the procedure. And a girl on the subway like passed me in a huff and like was kind of upset with me. And I was in such a good mood that I went up to a stranger, which you should not do in New York. And I was like, I'm sorry, did I bump into you? Like, did not mean that at all.
Corinne.
Like, I'm so sorry. I don't know why I did that. I've never done that in my life.
What
I've never done it
possessed you?
since.
Oh my God.
Who knows? She turns around and she goes, "Stay away from me, you crazy fucking bitch."
What?
So then something switched in me where I was like, I'm going to be crazy. I ended up not being crazy at all, but I just started thinking in my head like, oh, you want me to be crazy? Now I'm going to follow you home. I didn't do that. And that's like so much scarier than just like the ask of what's a petty thing you've done. But I was like, I'm going to like take a picture of you and just make you think I'm going to use it. So like I was losing my mind because I was like, you don't even me crazy. You're crazy. Clearly I'm the insane person.
I love the instantaneous
It was
rage
an instant
that you then
switch.
didn't act on.
Literally was in such a good mood. I did something crazy and then decided to go in the exact opposite crazy direction. Ultimately,
Yes.
the train came and I was on my way to work. So I just went to work.
You didn't follow her home?
No, but I was,
Wow.
and then I locked eyes with someone who was like, I thought that they were like, "Are you okay? That was crazy." But they were like, "Do you have $5?" I was like, "Here, I actually have $1." Like, this is, it was just like a series of New York thing after New York thing. So that was one of the craziest days of my life. But I
Wow.
wanted to be a petty bitch. I wanted to be mean.
It's satisfying. I think even just imagining the pettiness is also satisfying.
It was
Not
very
quite
satisfying
as-
to like indulge
Yeah.
the thing for a moment. I want to emphasize I did nothing. Like not only did I didn't do nothing to like influence her, but like decided not to be scary. Like I was like, I'm gonna move to the end of the train. This has nothing to do with me. But sometimes you just want to be horrible.
Yeah, it's true. I've been seeing, I think my TikTok FYP is trying to give me lessons in pettiness. It keeps showing me these videos of like women doing very creative things to get back at like men who have wronged them.
Yes.
And it's things like buy a bunch of spare keys and write his number on them and then leave them places so that people like call him.
Oh my God, I saw
to
one like
find
this.
them.
A
Yeah.
girl, she made a fake Facebook account to DM him Walking Dead spoilers
That's
because
good.
he called her and her friend like ugly at a club or something.
The lengths to which women will go
Yeah.
to speed up the whole karmic justice process.
That's exactly what it was.
We're like, karma's not working fast enough. We're gonna do it ourselves.
Yeah.
I think of myself as an internally petty person. Like I think it, but then I never do anything.
Yes.
Or I will just like revel in the karma that the universe has provided.
Yes.
Like my ex was trying to be a rapper before that ended. And I now have a job where I get to meet the CEOs of record labels.
Sure.
And like I'm literally going to London next week to like meet the heads of these record companies, and the petty colonel inside is like
Totally.
sucks for you. Like,
Totally.
but I didn't do anything. I'm just reveling in the petty righteous comeback that is already happening.
And that is way closer to being petty than like the people who are causing mayhem in the streets with like leaving phone numbers and DMing spoilers. But I love a story of someone being petty.
Yeah. Yeah. Oh, I'm a messy bitch who loves drama. Like it's true.
It's human nature.
Yeah. Yeah. So those are my 4 different projects. Like I said before at the top of the episode, my dissertation was like a stapled together collection of these different publications. And I wrote an introduction and a conclusion to make it clear how all of these projects helped me answer the question of, is there a galactic habitable zone? So my dissertation was titled, Why Are We Here? Question mark, colon, constraining the Milky Way's galactic habitable zone. And I actually opened it, like before my introduction, I had a little prologue, and I opened it with this story of 4 scholars getting together to discuss the question of why are we here? And one of them is a philosopher who's like, why are we here? What's the purpose? And then there's a geologist who wants to know, why are we here? Present tense. So what's special about now? And then there's a biologist who's like, but why are we here? What is it about our bodies that means we're the ones asking this question? And then the astronomer is like, okay, all of those are great questions, but the real one is, why are we here in this space right now? And so the rest of the dissertation tries to answer why we are here in this part of the galaxy. And I compared it to some previous work that had been done in the galactic habitable zone, but there really wasn't much. It was a field that some people were interested in the 70s and 80s, and then there was one paper that I could find from like 2001 that touched on it, and then nothing for 20 years. And even when I told my dissertation committee, when I told the faculty committee that this is the type of thing I wanted to study, at least one person in the room laughed.
Really?
Yeah, because it was kind of an older question that people, at least in the room, weren't interested in anymore. But I went back to those older papers and I compared my findings to theirs, and it seemed like we were all in agreement. Many of them had taken different approaches. Some of them looked at radiation, so like where in the galaxy will you be far enough away from dangerous radiation, and some of them took a time approach, like which types of stars last the longest and give life the most time to be successful. My approach was dynamical. I was looking at the way that stars moved around the galaxy to see how that influences habitability, but it matched what they said. So just the answer ended up being that we are apparently smack dab in the center of the Milky Way's galactic habitable zone. It is this ring around the center of the galaxy that starts at 7 kiloparsecs from the galactic center and goes out to 9 kiloparsecs. Our sun is 8 kiloparsecs away from the galactic center. A kiloparsec is 1,000 parsecs. We've talked about parsecs before, I think. But yeah, we're right in the middle of it. It's that ring, but then you also want to be around a particular age of star, and that is like older than 4 billion years, which our star is. So it was born like right around the right time. You want it to be slightly outside of one of the spiral arms so that it doesn't get caught up in that denser environment. And we are in the habitable zone for the galaxy, which is probably a sign that the conditions we're looking for are super like curated towards us, you know? But that was the dissertation. And then at the end of my dissertation, I actually had a whole extra chapter about my science communication work that I had done in grad school. And it talked about the history of science communication and the impact that I knew I had personally had, and a little bit about where I was going next. Because I defended in 2021, April, and I wanted to give them an example of a successful grad student who knew they didn't want to stay in academia.
Yeah.
Because I know there are going to be other students like that.
Right.
So now they have that to look at.
Oh, I'm so glad you did that. Cool.
So Corinne, my dissertation was called Why Are We Here? I'm gonna pose that question to you. Why do you think we are here? And you can answer that however you want.
Okay.
What's the purpose, Corinne?
I don't know. That's such a good question. That's the question. When things start to go wrong in the world, as they so often are, I'm like, wow, the only thing that matters is other people and treating other people kindly and loving each other. And I don't know what we do next or what our purpose is, but I feel like while we're here, it's really just to love. And that sounds so cheesy.
But true.
But true. And that's what academia is afraid to say.
Ugh. couldn't have said it better. On that note, let's just end it there.
Yeah.
So listeners, no matter who your favorite elementary school teacher was, you are space.
You are. And now we can go make a bitters and soda.
Yes. Let's do it.
Bye.
Bye. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.